And so we're doing spectroscopy in this course, and it teaches us about quantum mechanics because spectroscopy is really how we discovered quantized effects. You know, you had Bunsen's spectrometer that we used to determine the spectral lines of atomic spectra like hydrogen or helium. And so to do spectroscopy, you need the quantum system, you need the differences in energy levels, but you need some way of interacting with light. Light and matter have to interact. And so the matter has to be charged or magnetic to interact with light. So these are three requirements for spectroscopy. There needs to be an interaction with an electric or magnetic field. And most of the time that's with a charged particle. It interacts with the electric field. Or there needs to be some sort of charge distribution like a dipole moment where it can interact with an electric field. You need an unequal population of energy levels in order to detect the interaction. So if you have just as many molecules in the excited state as you have in a ground state, you might get absorption, you might get an emission, but you wouldn't know. So in order to detect the interaction, you need an unequal population of the energy levels. And then thirdly, you need a significant probability for the transition. So even if light matches that energy difference, and even if it's a charged particle, if it's a forbidden transition, then the probability is 0 that you'll have an interaction. And so today we're going to solve for that probability. So are all of these transitions possible? So these are the energy levels for a particle in a box. We have n equals 1 at the bottom, that's the ground state, and n equals 2, 3, and 4. And it goes all the way up into infinity. Okay. I've just superimposed the wave functions on there just to kind of show you what those wave functions are. As you go up and in, you see that you have an increase in the number of nodes because curvature is kinetic energy, and so as you have an excited wave function, you have more curvature, you have more nodes. And so are these transitions probable? Let's go through our checklist. So 1, we have charged particles. We have an electron confined to a small space. 2, we have an unequal population. What tells us that population? Do you remember the function? We've covered it several times in these lectures. Yes, it's the Boltzmann distribution. That tells us the thermal population of these energy levels. That's the piece that's temperature dependent. Okay? What do you think happens to all of these particles in the excited state if I cool the system down? They go down. They go down to the ground state. So if I put this at close to absolute 0, I would only have molecules in the ground state. If I really heat this up, then I'll have molecules in the excited states. So I have unequal populations because the Boltzmann distribution favors the ground state, but it'll tell me at whatever temperature I might have 2 or 3 molecules in the excited states. And so I do have unequal populations. Even at absolute 0, they're all in the ground state and not in the first excited state, so that's still an unequal population. I could see very good spectra from n equals 1 to n equals 2 at absolute 0. And that simplifies things because I don't have any other excited states to worry about. So a lot of times we try to do spectroscopy at really low temperatures to simplify things and to learn about the molecules or atoms. And then the third one is probability. Every one of these arrows connects 2 energy levels. Are they all allowed? We don't know until we do the integral. So that's that transition moment integral, is this transition probability. Okay? So we could go from 1 to 2, 2 to 3, 3 to 4, or maybe 1 and skip a level, go 1 to 3, or 2 to 4, or maybe jump all the way to 4 from 1. Now there's a bunch of other possibilities if I showed n equals 5, n equals 6, and so on. But this is plenty for one slide. Okay, it's pretty busy. And then emission is on the right. What can we jump down? Like if we have molecules in the excited state, can they jump down? We'll see it's the same integral. So we have the spectroscopic transition probability. We have the Boltzmann piece in blue. That's the temperature dependence that tells us about the unequal populations. And then we have the transition moment integral. So this is the transition moment integral here. For absorption and emission, we call it the transition dipole moment because it's just a single photon of light It's a dipole, electric dipole. And so this is the integral in Dirac notation, and here it is sort of spelled out with the regular integral dx. So this piece right here is the same as this piece. It's in red. Okay. And so that's that sort of acronym. Absorption is big. It's Boltzmann times I, which is that transition moment integral, I for integral, and then G for line shape, the Gaussian line shape. We're not going to deal with the Gaussian line shape because if the probability is 0, you won't have a peak. If the probability is high, you'll just have a curve on there, a Gaussian curve on top of that I, that integral result. So why do we use X to represent light? Well, we want the maximum effect. And light's an oscillating electric field. It also has a weak magnetic field at 90 degrees. And so if we, let's do this. Can you draw an E on my computer? Can't do that by myself. So it has an electric field that oscillates up and down. And it has a magnetic field 90 degrees. It oscillates up and down. So this is maximum electric field, maximum magnetic field. Maximum negative electric field, maximum negative magnetic field. So north, south, positive, negative. And so it's doing this. Okay. Go, team, it's like a cheerleader. All right, so it's this oscillating electric field that's going to interact with our charged particle. And we're going to put that on the x-axis because we only have one dimension in our particle in a box. We'll put that electric field as maximum as it can be on the x-axis, and so we'll just use the x-axis because it has a positive side and a negative side, or from your perspective, a positive side and a negative side. So the x-axis, mathematically, serves the function of the electric field in light. It has a positive end and a negative end. That's all we're using it for. And so is it going to give us the exact probability? No, we're just looking at relative probabilities. So it's good enough. It doesn't have the units of electric field. That's okay. We're just integrating that interaction with our wave function, and we're saying that intensity is proportional to this integral squared. Since we're using proportionality, this peak versus that peak, we don't have to have the exact result. We just need to know that this probability is twice this one, and we'll be able to model the spectrum. To get the exact number, we would have to know exactly how many atoms were there. We're not going to know that either. So it doesn't make sense to try to be so exact. Proportionality is good enough. And so we'll just use that x-axis as our light. So that thing in the middle is our photon of light acting on our wave function, and then we sandwich it with the other wave function, the complex conjugate, integrate over all space. We might get a negative result. We square it, and everything's positive. Okay. And it's proportional to the square of that integral. So that's what's going on with that x in the middle. And that's why when we're doing scattering, we have two x's. We have two photons of light, x squared. And that's as complicated as it gets. We're going to have x for absorption or emission, and x squared for scattering. So these are the results. So in your lab, if you use an electron in a 7 angstrom box, then you should be able to verify these numbers by hand. When you put in that L and you put in the mass of the electron and Planck's constant and everything, for 1 to 2, you should have 1298 when you do that integral and you square it. For 2 to 3, you should have 1514 as your relative probabilities. Notice these don't all sum to 1, they're just relative probabilities. So these are some interesting results. Notice 1 to 3 is 0 and 2 to 4 is 0. So even though I have this x times this wave function times the complex conjugate integrated over all space and squared, those are all sine integer multiples of pi, and everything is 0 when I do that calculation and end up with a probability of 0. So this is telling us that it's not allowed to go from 1 to 3. even if I have a charged particle in one, even if there's an unequal population and light actually matches that energy difference, that particle will just stare at light and say, pass on through, I can't go there. My probability is 0 for jumping 2 levels. Okay, that's nice because in the spectrum, those peaks are missing. That would really complicate things if every peak was possible. And so we see simple spectra that can't really be explained because we've got a complex quantum mechanics system, but these probabilities take away some of the results. And we'll see examples of this in the lab throughout the semester. Here's another interesting result, that absorption, 1514, emission, 1514. And so this tells us that whether I have wave function 2 on the right and 3 on the left, or those are swapped, the integral results the same. And so one is absorption, the other is emission. Now by convention, we have the lower state on the left. No, by convention we have the lower state on the right and the upper state on the left. So notice that 2 is on the right and 3 is on the left and the arrow's going up. So that's an absorption transition from 2 to 3. And then by convention, the lower state, the initial state, I should say, the initial state is on the right and the final state is on the left. That's the correct language. Because here, the initial state is 3 and the final state is 2. And so we're going from 3 to 2, so that's an emission transition. This is going from 2 to 3. Initial state is 2, final state is 3, so we're going up. And so that's an absorption. That's the way I write all of these because that's the way it was taught to me, is sort of the tradition of writing these transition moment integrals, initial and final. Initials on the right and finals on the left. And then finally, we can skip from 1 to 4. That's a change of 3 quantum states. So we can jump by 1 or we can jump by 3. We cannot jump by 2. So jumping by 3 is allowed. That's a non-zero integral, but look how much less probable it is. And compared to 1200, 1500, it has a probability of 8.3. So it's possible, but it's not very probable. What we see in these patterns are called selection rules. So changes by 1 quantum state, so delta n equals 1 is an allowed transition. Delta n equals 2 is not allowed. Delta n equals 3 is allowed. So we know a couple of those selection rules. So this is an important vocabulary word, selection rules. It's the changes in states that are allowed. So the selection rules, everybody write that down. Selection rules are important. And they're the allowed transitions. And you use the quantum numbers to decide, you're using the quantum numbers to define your selection rules. So delta n equals 1 and 3. Those are the selection rules for absorption and emission. And even though we don't know about 5, 7, and 9, those are allowed too. So all odd jumps are allowed for a particle in a box. It's specific to the system. So particle in a box, 1, 3, 5, 7, 9. Those are, and on up. Those are the selection rules. Meaning, those are the allowed transitions. So we focus on the ones that are allowed. And by elimination, the ones that aren't allowed are the ones that are forbidden. So it's forbidden. 2, 4, 6, 8, even jumps are forbidden. Now I did these calculations in Excel. It takes, quite a large sheet of Excel formulas to do this. You're doing this by hand in lab. Has anyone done a selection rule calculation or at least a transition moment integral yet? You have? How many pages was it?
Like a whole sheet back and forth.
So 2 full pages of math. Anyone else? How about you? 9. So you showed all your level. You write small. So from 2 pages to 9 pages of handwritten math to do those integrals and simplify and clean things up. And we will see when we get to symmetry, we can do it on a Post-it note. We can get the selection rules from a Post-it note. Okay, so that's a little foreshadowing on the symmetry and why I like symmetry. Okay, if I can get rid of 9 or 2 full pages of math and just do this on the back of an envelope, then I've found a useful tool. So we now know the intensity of the peak. We can calculate the Boltzmann distribution. That's just that simple formula with evaluating the energy level over KT. We haven't done much with the Gaussian. That's fine. We'll use that when we get to spectral simulation. But these transition moment integrals was this piece right here. That's I, right? So that's that integral piece that we just solved. So that tells us how tall the peak is. That's the probability of that peak. That tells us how tall the peak is. If it's 0, there's no peak. So the forbidden peaks don't show up. The allowed peaks show up. Okay, but that doesn't tell us the peak location. The peak location comes from the differences in those energy levels. That's the transition equation. So far we have transition moment integral is the intensity. So you write that down. Transition moment integral is the intensity. Transition moment integral is the intensity. And sometimes the word dipole is in there for absorption and emission. For scattering, it's just the transition moment. So now we will do some algebra that is totally appropriate for me asking you all kinds of questions on the homework and the exam. Okay, trying to find where this peak shows up is the transition equation. So this transition equation, we have the word transition in both of these. This one tells you where the peaks are on the x-axis. Transition equation tells you where the peaks show up. Not how tall they are, but where they show up in the x-axis. So let me simplify that. The transition equation tells you where the peak is on the x-axis, or horizontal axis, in a spectrum. So the transition equation tells you where the peak is on the horizontal axis in a spectrum. Last time, the transition equation tells you where the peak is on the horizontal axis in a spectrum. And you can actually solve for this. Once you get the Schrodinger equation, it tells you what the energies are, and you can just take the differences in energies. Now, I like to do this instead of taking the energy of n equals 2 and subtracting energy of n equals 1, and then doing the same kind of calculation with 3 minus 2, 4 minus 3. Let's do all of them at one time. So let's say n to n plus 1. So all of the changes of delta n equals 1. We can do those algebraically, and we can solve for all of those transitions where the selection rules are plus or minus 1, plus or minus 3, plus or minus 5. So we can solve for the transition equation going from n to n plus 1. And that will handle the energy difference from 1 to 2, 2 to 3, 3 to 4, all of those changes where it just jumps one level. So this is a skill you need to have. This is the delta E for all delta n equals plus 1s. So you just take that energy equation that has a function of n, and you, wherever there's an n, you put an n plus 1. So can you see that? There was n squared, right? And I take n plus 1 squared and subtract the energy equation where it's just n squared. So we're going to get a general transition equation that tells us where all of these peaks show up on the horizontal axis. It's a very important skill in spectroscopy, is to be able to solve for the transition equation. We can take this equation straight to the spectrum and solve for molecular properties. So this is simplification. We just take all of the h squared, 8ml squared out in front. And we're left with this polynomial in n. Pretty simple to do. Go back to 8th grade algebra. I'm going to kind of go a little faster than maybe you can write, but these are posted on Blackboard, so you can go back through. And I would, if I were you, go through and work these in my notebook just to make sure that I've done it with my own hand. Okay. So n squared plus 2n plus 1 minus n squared. And so it simplifies to this. We have this piece out front times 2n plus 1. Okay. A lot of times that 2n is pulled out and it'll be n plus a half. And then over there we'll cancel that 2 with the 8 and have 1 over 4. So let's now see what this, well, let's do one for n plus 3, right? It can go up by 1, it can go up by 3. So what's the transition equation? Well, actually I did the simplification here. You'll see why I left it in this form. I left that h squared over 8ml squared alone. So there's a 2 in front. This right here will serve as a nice little constant that we'll see in the next equation too. So let's do the transition equation for n plus 3. And so on your test or homework, you know, I may ask you to do n plus 9. Okay, so you need to be able to do this type of algebra. It's pretty simple. But if you haven't focused on that, then you might have a hard time. The first time you try this is on the exam, then you're going to have a hard time. Okay. So let's do the n plus 3, delta n equals plus 3 transition equation. So wherever there's an n, you put n plus 3, straightforward. Simplify that, we have a different polynomial, but it's pretty similar. And now we have 6n plus 9 in the middle, the n squareds cancel. And so I still have that same constant out front, h bar squared over 8ml squared. I'm going to go pull that 6 out. And so I end up with 6 times that constant times n plus 2/3. And so this is the transition equation for the overtones, the jumps where it's not just to an adjacent level, but jumping by 3 units of 3 quantized units. And so this tells us on the horizontal axis where these peaks are. And they're going to be labeled with the lower quantum number because we went from n to n plus 1 or n to n plus 3. And so n is that lower state quantum number. And we can label those peaks by that n.
So if we were going from 3 to 9, like you said, would 3 become n and 9 become n plus 6?
Yes, yes. Yeah, so whatever you're starting at, we're just dealing with absorption. Emission would be the same kind of thing. But we'll just focus on absorption because it's easiest at this point to understand. We're absorbing light and it's jumping up. Okay. So this is the spectrum that we would get. I've put in the intensities that I got from Excel. And so where are these, you know, how would we assign these peaks? The blue series is delta n equals plus 1. The green series is delta n equals plus 3. That was the 1 to 4 transition. And the 2 to 5, and the 3 to 6. So all of those green ones are jumping 3 levels. And then the 5s are on there, the red ones. And notice how the 3s and the 5s are really tiny, probabilistically. They're really short, small peaks compared to the blue ones. So jumping by 1 is definitely more probable than jumping by 3 or 5. I didn't even show the 7s. So that first peak is called the fundamental. There's a vocabulary word too. The fundamental transition is the lowest energy level. It's that very first allowed transition. Because even at absolute 0, the fundamental will still be there. Notice I can't go from 2 to 3 if there are no atoms or molecules in state 2. So at absolute 0, everything's in the ground state. So you still have the fundamental. You'll have a 1 to 2 transition, but you won't have a 2 to 3 because there are no molecules or atoms in state 2 because we've cooled it down to absolute 0. So you'll always have the fundamental transition. Yes?
Is the fundamental transition always going to have the same intensity?
It'll have the same transition dipole moment. Yeah. But if we cool it down, think about the Boltzmann factor. If I stuff more molecules in that ground state, then its intensity is going to go up. So all those other other transitions will drop in intensity as I'm cooling it down, and the fundamental will get huge.
Okay.
Yeah, and so all of the molecules are in the fundamental. So that's, again, helping your sensitivity. You can really see that transition at very cold temperatures. So cooling things down really helps spectroscopy, unless you're trying to see the excited states. So that fundamental transition is that very first one. That's the 1 to 2 transition in our exercise. When we get to vibrational motion, we actually have a V equals 0, a 0 state, and so it'd be 0 to 1. It's just that first possible transition. Then these others are called hot bands. So the 2 to 3, the 3 to 4, the 4 to 5. And can someone explain to me what's meant by hot band? Remember I said the fundamental is always there even at absolute 0. So these are only there when it's hot, when the thing is excited to a temperature where I have molecules in the state 2, state 3, state 4. So the hot bands only happen when you're at an appreciable temperature above absolute 0. So the molecule system or atom system has to be hot for these transitions to show up. And hot is relative. You're talking about helium, liquid helium or something. It's going to have lots of hot bands. But if you're talking about, say, the CH stretch and vibrations, that first excited state is at 3,000 wave numbers, and at room temperature you only have 200 wave numbers of energy. So you're not going to have any hot bands for that CH stretch. And then these others, because we're skipping a level, they're called overtones. So the change in 3 or 5 quantum states, those are overtones, where you're jumping levels. And the overtones are not very probable. You can see that. So it's pretty rare that you'll see an overtone in a spectrum. Sometimes you're looking at a spectrum, you see a little peak in the, in an unexplained place, because the equations for all these delta n equals 1 or 2, changes by 1 quantum state, and those are, most easily understood when you're assigning a spectrum. And then you see this little bump, and you think, what is this little bump, right here? Let's say you've got a spectrum that looks similar to this, and you see all these hot bands, and then between these two peaks, you see this little bump there, and you're like, well, that's weird. What is that? Well, it's an overtone, okay? And if you have a really good, clean spectrum, high resolution and low noise, you see this little bump there, you may need to explore. Maybe it's an overtone, and that's how you find them sometimes. It's some unexpected peak, because you really don't see them very often. Yes?
Why is the second transition higher than the intensity? Why is it higher than the fundamental?
That's a great question. It just works out with that transition dipole moment integral. In fact, let's go back, because that's a good question. Let me back up to that Excel sheet where I showed all these. If you'll notice, the 1 to 2 is 1298. Then the 2 to 3 is 1514. And then the 3 to 4 is actually higher than that. It's 1576. And so the overlap of these wave functions actually gets better when you have more kinetic energy. You see those lobes interact with each other better. It doesn't continue to increase dramatically. It kind of tapers off, but it does increase. For the particle in a box, it increases. So the other question is, if the 3 to 4 is higher than the 2 to 3, why is that peak drop back down? See, so from the first peak to the second, it goes up. And then from the second to the third, it should go up again, but it goes down. And it's going down because of the Boltzmann distribution. So there's fewer particles there in that third state. So you have two things competing. This goes up like that because of I, but it goes down because of B. And so for that first one, that increase in I counteracts the decrease in the Boltzmann distribution. But then after that, the Boltzmann distribution takes over and it all drops down to 0. Yeah. So it's very observant. Good job. So we can assign transitions to every one of these peaks. So that's what this next or that, or if we take notice the x-axis is transition energy, okay? But what if we take it where it says wavelength? Energy and wavelength are inversely proportional, so we flop that. Oh, and let's go ahead and show the transition equations on here. So we have in blue that 2 times that constant times n plus 1/2, and then the green overtones has 6. Notice how the green peaks are spaced further apart. That's that factor of 6 that you're seeing. So the blue are spaced 2 times that constant. The overtones are spaced 6 times that constant. What about delta n equals 5? I'll leave that to you on your own to figure out what that spacing is. Notice it's further than the green. Okay, but you can figure out what that relative spacing is in the delta n equals 5s. Now if we flip the x-axis, we're plotting versus transition wavelength. And notice how doing something in wavelength really separates that fundamental from all of the hot bands and overtones. And so that's another reason why we like to take spectra in wavelength, because it really separates that fundamental from the rest of the pack. And so here are all the peaks labeled with their quantum states in the transitions. So if you were to get this spectrum without those numbers, could you put the numbers on there? That's a good question to ask yourself. Okay. The lowest energy difference would be the 1 to 2. Then the next energy difference, the next peak would be 2 to 3. And then the next one, 3 to 4. And it just marches up. You see that? And then the first overtone, what is that one? It's 1 to 4. Okay, but then the second one, this is the most common mistake. When they label the second overtone, they start at 4 and go up. That's not right. I go 1 to 4, and then I go 2 to 5. So there's an overtone starting in level 2. And then there's an overtone starting in level 3, going to 6. You see the pattern? Okay. And then what about the delta n equals 5s? It's still an overtone. We really don't have a name. I guess you might call it super overtone or something. I don't know. But it's those delta n equals 5, so it's going 1 to 6, and then 2 to 7, and then 3 to 8. Differences being 5. So this is what we call an assigned spectrum. It's assigned with all the quantum numbers. Okay. Any questions about this? This is really the goal of spectroscopy, to take those peaks and actually know what's going on at that transition. And this is the difference between analytical chemistry and physical chemistry. Analytical chemistry is mostly interested in the peak maximum and how it relates to concentration. Right? Beer's law. So you go in and you're using spectroscopic tools to figure out concentration, abundance, maybe kinetics, and so on. But you're not really asking the question, what's happening at that peak? What quantum states are involved? Is it a vibrational transition? Is it an electronic transition? Or is it all of the above? Whereas physical chemistry is trying to get into the physical properties, what's happening to the system with this interaction with light. And so I'd like to say analytical chemistry is focused on the y-axis, and P-Chem is focused on the x-axis. Why is that peak there and not there? And what does that tell me about the molecule? And so here's the assignment using in wavelength form. So that fundamental is the 1 to 2. The first hot band is 2 to 3, 3 to 4, etc. And then all of those overtones are buried down into the low end of the spectrum, the short wavelength side. And if this is invisible spectroscopy, all of those overtones and things do absorb light, even though each one is not very probable. When you stack them all on top of each other, there's lots of ways light can be absorbed, and so you have that solvent cutoff. If you're doing a spectrum in a UV vis spectrometer, eventually you reach the spectrum absorption of your solvent, and it just absorbs to infinity. No light gets through. And that's what's happening down at that short wavelength part of the spectrum, is all of your overtones are taking over and you're getting absorption. And it's blocking all of the light. And so taking that transition equation and writing it in terms of wavelength, then we have this 4 pi L squared C over H, and N plus 1/2 is in the denominator. And so as N gets bigger, you see the wavelength gets shorter and shorter and shorter. But what's nice about this is if you have the transition, the fundamental transition, and you have the mass of the particle, you could solve for L, right? What is then interesting about that? Well, let's say I've got a spectrum of an electron, and it shows up at 420 nanometers, that fundamental transition. You know Planck's constant, you know the speed of light, you know the mass of the electron. Now you know what the confinement space is for that electron. You can solve for L. Just from the wavelength of that fundamental transition. And again, that's a physical chemistry question. Let me learn about the system by taking a spectrum. I get a peak at 420 nanometers of an electron. How tightly constrained is it? What kind of space is it in? You could solve that using this transition equation. So that's it for